In the early 1970s, NASA began building a new idea into a spacecraft: repetition. The Space Shuttle was designed not as a one-time rocket, but as a reusable vehicle that could fly again and again. That promise mattered. If it worked, spaceflight stopped being rare and experimental and became something closer to routine. The plan depended on fast turnaround, predictable performance, and a system that looked dependable to the outside world. That vision also changed what success meant. A shuttle launch was no longer only a technical event. It was a schedule item, a budget promise, and a public expectation. Reusability sounded like savings, so planners built timelines around frequent flights. Each delay threatened more than a date on a calendar. It threatened funding, credibility, and the argument that the shuttle was the future. Pressure did not arrive later. It was built in from the start. As designs took shape, the program became a balancing act between what engineers wanted and what the program needed to claim. The shuttle had to be advanced, but it also had to be affordable. It had to be safe, but it also had to fly often. Those goals pulled against each other, quietly shaping choices long before anyone watched a countdown. Over time, the system learned to treat performance promises as commitments, and commitments demanded proof launch after launch. With the shuttle's design taking shape, the solid rocket boosters became a make-or-break choice. They delivered huge power, but they also depended on a simple idea: a tight seal between metal sections that had to hold back burning gas. That seal came from O-rings, rubber loops meant to compress and block any leak. In early tests and inspections, engineers noticed troubling hints that the rings did not always seal the same way. The warnings looked small at first: a trace of heat on a ring here, a mark that suggested a puff of gas got past the first barrier there. Engineers wrote it down, compared results, and debated what it meant. Some conditions seemed to make the seal less reliable, especially in the first violent moments after ignition. But the hardware still appeared to work overall, and the problem got labeled as something to watch, not something to stop everything for. Then the shuttle began flying real missions. After each flight, teams examined the booster joints, logged what they found, and filed reports on erosion and unusual wear. The launches kept happening anyway, and that routine mattered. Each successful landing made earlier anomalies feel less urgent, even when the seals showed signs of stress. A pattern took hold. If the system flew and came back, the risk felt acceptable. The abnormal became familiar. In 1985, the warnings stopped looking like isolated quirks and started looking like a pattern. After certain shuttle flights, inspections of the solid rocket boosters found clear signs of damage inside the joints. The O-rings, meant to seal hot gases under extreme pressure, sometimes showed erosion. Even more troubling, there was evidence of blow-by, meaning hot gases had slipped past the seal. That was not a near miss. That was the seal failing to do its job. These findings mattered because the booster joint did not get a second chance once ignition began. The seal had to work immediately, in the first moments of the launch, when pressure rose fast and metal parts shifted under load. Erosion and blow-by proved the joint did not always seal in time or seal fully, yet flights continued. Each post-flight report added another data point showing the same basic flaw could repeat. The system kept operating with evidence that its safety margin was thinner than advertised. By the end of that year, the program lived with a new reality. The boosters flew with a known defect that appeared again and again. There were discussions, proposed fixes, and ideas for redesign, but nothing fully implemented that removed the risk at its source. The O-rings remained the same basic answer to the same basic problem. The danger was not hidden in theory anymore. It was written into the hardware after each flight, in burned material and soot trails where hot gas went where it never should have gone. Launches had once been treated like rare events. Now they had become a steady drumbeat, and the shuttle sat closer to the centre of national plans. With each flight added to the manifest, the schedule tightened its grip. Delays no longer looked like caution, they looked like failure. In that climate, engineering concerns started to land on managers' desks as obstacles to clear, not warnings to stop for. The paperwork grew, but its meaning changed. An engineering note that once demanded action could now be managed through wording, routing, and signatures. Risk became something to process. The deeper shift came in how safety got argued. It no longer required proving a system was ready. It required proving it was dangerous enough to justify slipping a launch. That burden quietly flipped. So the discussion moved from fixing the hardware to defending the schedule. Concerns still got written down, but they got framed as uncertainties, not as reasons to halt. Each successful launch under known problems made the next one feel easier to approve. That was the trap. The shuttle kept flying, and the standard for stopping it rose higher and higher, even as the evidence piled up. By late 1985, the warnings around the booster joints stopped sounding vague and started sounding specific. Engineers looked at the O-rings and saw a simple physical problem. In the cold, rubber stiffened. It did not spring into shape as quickly. That timing mattered because ignition happened fast. The seal had to respond instantly, or hot gas found a gap. A known flaw now had a switch that could flip it into disaster. Flight evidence began to line up with that idea. When temperatures dropped, the marks left behind in the joints looked worse, not better. The O-rings showed deeper erosion and clearer signs that hot gases had pushed past the first barrier before the seal recovered. That meant the system sometimes relied on a delayed second chance to seal itself. And in a rocket motor, a second chance came too late. Cold did not create the defect. Cold made it active. That shift changed everything about the risk. Until then, the joint problem lived in reports and post-flight inspections, serious but abstract. Now it had a trigger anyone could understand. Low temperature at launch. It offered a straight line from conditions on the pad to what happened inside the joint in the first seconds of flight. The danger was no longer just that the O-rings sometimes failed. The danger was that one cold morning could make failure far more likely right at ignition. By late January 1986, the next shuttle launch sat on a tight calendar, but the weather forecast broke the routine. The overnight temperatures dropped far below what the booster seals had faced before. Engineers treated that cold as more than discomfort. They treated it as a direct hit to the one part already known to be vulnerable. If the O-ring stiffened, the joint could leak at ignition, and that leak could become fatal. The engineers did what they could with the evidence they had. They pulled flight history, compared it to temperature, and built a worst-case argument instead of a comforting average. The pattern looked simple. Colder launches lined up with deeper seal damage. But the data set stayed small, and the trend did not look clean enough to end the debate. That uncertainty mattered because the burden shifted onto proving danger, not proving safety. The decision narrowed to a teleconference that linked NASA leaders with the booster contractor. It became the moment where technical caution met schedule reality. A delay threatened the launch manifest, public expectations, and high-level commitments already made. So the discussion turned into a test of how risk got framed. Engineers pushed for delay because the cold removed their margin. Management pushed back because the case sounded incomplete. The final call now hung on that argument. Management overruled the engineers, and the countdown continued. On January the 28th, 1986, Challenger lifted off in the coldest conditions the shuttle had ever faced. That detail mattered immediately because the booster joint seals depended on quick, tight contact. In the cold, the rubber responded more slowly. Ignition pressure rose fast, the joint flexed, and the sealing system did not keep up. The risk became a physical event. As the boosters pushed the vehicle upward, hot gases found a path at the flawed joint. The first seal failed to stop it, and the second seal did not provide the backup protection it was supposed to. That was the design's last line of defense, and it was already compromised by the temperature and the joint's movement. Once the leakage began, it did not need a new mistake to grow. It only needed time and pressure. Challenger kept climbing, and the system behaved like it was working, but the damage had started. The joint sealing could not recover during flight because the forces on it only changed and intensified. Each moment of ascent loaded the structure again, and the leak path stayed open. The chain of events became one way. A decision made on the ground turned into a failure in the air, and there was no practical way to stop it. 73 seconds after liftoff, the flight ended in an instant. Challenger broke apart high above the Atlantic, and the mission never had a chance to recover. The 7 people on board died. For families, for co-workers, for anyone watching, it landed like a physical blow. A program sold as dependable suddenly looked fragile, and in that single moment, years of confidence collapsed with it. NASA could not treat it as an accident to move past. The shuttle program halted. Launches stopped, schedules fell away, and the central question became brutally simple. What exactly failed, and why? Engineers and managers faced a new kind of pressure now, not to fly, but to explain. Every detail of the ascent mattered. The smallest technical weakness and the smallest decision both became suspects. The search for a cause moved on 2 tracks at once. One track followed hardware, the boosters, the seals, the moments when the vehicle was still intact and physics could be traced. The other track followed behavior, how concerns got handled, how risk got described, and how a launch got approved. Challenger forced NASA to confront a possibility it resisted for years. This was not random. It was built. The investigation moved fast, and it moved with purpose. A presidential commission, later known as the Rogers Commission, took testimony, reviewed records, and pressed for a clear chain of cause and effect. It did not stop at the breakup in the sky. It followed the failure back into the hardware. The evidence kept pointing to the booster joints, where O-rings were supposed to seal hot gases, and did not. As the commission dug deeper, the problem widened. The O-ring failure did not look like a sudden surprise. It looked like a known weakness that had been lived with. Flight after flight had produced erosion and blow-by, and those warnings had been absorbed into routine. That pattern had a name: normalized deviance. Risk had been discussed in ways that softened it, and management pressure had pushed decisions toward launching. The findings forced NASA into a hard pause. The shuttle stayed grounded, and there was no path back to flight without change. The booster joints had to be redesigned, so sealing could not depend on perfect timing and perfect temperature. But the Commission also pointed at the system around the hardware. Safety and engineering voices had to carry more weight, risk communication had to become blunt, and launch decisions had to change before the next countdown. In the years after Challenger, the disaster settled into something bigger than a single failed part. It showed how a large organization could slowly train itself to live with warning signs. Each time a problem did not immediately cause a loss, it started to feel normal. Risk stopped feeling like a red light. It started to feel like background noise. That shift, more than any one decision, became the true danger. NASA responded with redesigned booster joints, tighter rules, and safety officers meant to keep engineering reality from being pushed aside again. Flights eventually returned, and the hardware performed differently. But the deeper questions stayed. New structures could not automatically change old habits. Paperwork could still replace understanding. Pressure could still blur judgment. The system looked stronger, yet the lesson remained that safety depended on people staying willing to hear bad news. Over time, Challenger became a reference point for anyone who managed complex, high-stakes work. It marked the moment when the promise of routine access to space collided with the reality of a machine that demanded respect. The program began with confidence and a belief in predictability. It ended with a warning stamped into history. Ignored engineering limits did not just raise risk, they converted ambition into tragedy.